All right, let's jump right in. We're going to take a trip back to 2015, which, feels like a different century in AI years, to check out a blog post that showed off something kind of magical about a tech called Recurrent Neural Networks, or RNNs. This was a really big moment, and today, we're going to unpack exactly why. And hey, don't just take my word for it on the whole magical thing. This is a direct quote from the source of our explainer today, a really classic post by Andrej Karpathy. It just perfectly captures that feeling of seeing something you're pretty sure shouldn't be possible actually happen. I mean, just look at this. It looks like a page torn out of a super advanced math textbook, right? You've got lemmas, proofs, all that complex notation. But here's the wild part. This was written by an AI that was just fed the source code of the textbook. That's it. It figured out the language of mathematics completely on its own. So yeah, that brings us to the million-dollar question. How on earth is this possible? How does a machine go from just seeing a long string of characters to generating really complex, structured stuff like computer code, Shakespearean dialogue, and even math proofs? Well, we're about to pull back the curtain.
The secret ingredient, the key to this whole shebang, is a special kind of neural network, one that can actually remember things.
Okay, so here's the main difference you need to get. A normal neural network is kind of like a calculator. You give it one fixed thing, like an image, and it spits out one fixed answer, like the word cat. But a recurrent neural network, that's totally different. It's built to handle sequences of data. It's less like a calculator and a whole lot more like a computer program with an internal memory that keeps track of what it saw before. And this diagram just shows you how incredibly flexible that idea is. See, RNNs can take one thing and generate a whole sequence, like writing a caption for a picture. Or they can slurp up a sequence and give you one answer, like figuring out if a movie review is positive or negative. Or they can do what Google Translate does, take in one sequence and spit out a totally different one. This ability to work with sequences, that's its superpower.
And this quote just nails it. With RNNs, we're not just trying to find the best simple formula to turn A into B. We're actually, in a way, searching for a program that can process information as it changes over time. That's a huge leap in what these things can do. Okay, so we know what they are now, but how do they actually learn? Well, the method is almost shockingly simple, but as we'll see, it's unbelievably powerful.
So the specific model we're digging into is called a character-level model. Its entire job, and I mean its only job, is to do one thing, read a bunch of characters, and guess what the very next one is going to be. That's it. We don't teach it about words or sentences or grammar. It has to figure all of that out from scratch.
So the process is a lot like teaching a kid their ABCs. You show it the letter H, the network takes a guess at what comes next. Let's say it guesses O. We correct it and say, nope, sorry, the right answer was actually E. The network then makes a teeny tiny little adjustment to its internal wiring, just to make E a little more likely next time. And then you do this millions and millions and millions of times. You can actually see it in action right here. The network is being fed the sequence H, E, L, L. And at every single step, it's making a guess. It's calculating the probability for every possible next character. The whole goal of the training is to just nudge the network so that the probability for the correct letter, which is that green number you see, gets a little bit higher every single time.
So, what happens when you take this really simple method and just let it run on huge, complicated sets of text? Well, you get some results that are honestly pretty mind-blowing. So, first up, they trained the model on a bunch of essays by the programmer Paul Graham. Now, the text it generated is, well, it's kind of nonsense, but it absolutely nails the style. It learned how to use punctuation, the average sentence length, even the kinds of words he uses. It has the vibe of one of his essays, even if it doesn't actually make any sense. Next, they fed it the complete works of Shakespeare. And just look at this. It learned to write in that old-timey English. It learned the vocabulary. But the most incredible part? It learned the structure of a play. It generates a character's name in all caps, and then it writes their lines. It figured that out just by reading.
When they trained it on raw Wikipedia articles, it didn't just learn how to write encyclopedia entries. It learned the formatting code behind the page, called Markdown. It just started spitting out headings and bullet points and even links with the right syntax, all by itself.
Okay, but this is the real test, right? Essays and plays have style, sure, but computer code has strict, unforgiving rules. There's no way a model that's just predicting characters can learn something that complicated. Can it?
Well, the answer is a big fat yes. They fed it the source code for the Linux operating system, and the RNN started writing C code that looks shockingly real. It gets the syntax, the curly braces, the indentation, even the comments. Yeah, okay, it has some bugs, like that part where it checks if a variable is equal to itself, but the fact that it learned the structure at all is just staggering.
So we've seen the pretty amazing output, but what is actually going on inside this thing? Let's pop the hood and see how it's keeping track of all these complicated rules.
This is where it gets really, really cool. If you peek inside the network's memory, you can see that individual little neurons have basically taught themselves to do specific jobs. This one neuron here, the one in green, it's become a URL detector. It reliably turns on whenever the network is reading a web address and turns off as soon as it's done.
And check this one out. This cell learned to keep track of whether the model is currently inside a set of quotation marks. Just think for a second how useful that is for predicting what comes next. The network isn't just copying text, it's building its own little internal tools, its own state trackers to help it do its job better. Nobody told it to do this. It just emerged.
And as Karpathy himself put it, this emergent behavior is one of the clearest examples we have of where the real power of these deep learning models comes from. They don't just memorize patterns, they learn to create their own abstract concepts to understand those patterns.
All right, so let's zoom out. Let's put this little 2015 experiment into perspective. Why was this simple-sounding task of predicting the next character so important for the history of AI?
Well, it was a huge deal for a few big reasons. First, it showed that a really simple goal could lead to amazingly complex behavior. It proved you didn't need to hand code the rules of grammar for a computer. A network could just learn language, syntax, and structure right from the raw data.
This work, you guys, directly paved the way for the giant LLMs and transformer models we see everywhere today. It even gave us a little hint to future concepts like attention that are now central to modern AI.
And that really brings us to the final thought here. If this was the kind of magic that was possible almost a decade ago with a pretty small model whose only job was to predict the next letter, it really makes you stop and think about what's being built on these foundations right now and what kind of magic is waiting just around the corner.